Yes, everything okay.
Oh, all right. Well, it is my pleasure to participate in this conference. I'd like to thank the organizers and for the invitation. And I think one of the things that while we all miss some in-person capabilities during our time of pandemic lockdowns, nevertheless, the ability to participate in international forums like this is really grown, and I think it's a good thing that I hope we at least keep doing in some respect. And at the very least, I think we can think about how much we've saved on energy, our carbon footprint. All of those things are very good. All right, so back to chemistry, and as the British comedy group Monty Python once said, and now for something completely different. We're going to talk about some homogeneous catalysis chemistry. And while it isn't in the catalysis bent, if I have time, I will talk a little bit about the biological activity of some of these same compounds so that we can actually get two kinds of activities. We can get biological and catalytic. All right, so what I want to specifically talk about today and recognize the contributions of recently minted PhD, Dr. Chad Bernier, for much of this work. We're going to talk about using some N-heterocyclic carbene ligands in this chemistry. We're going to see the synthesis and catalytic activity combining iridium NHC and amino acid for asymmetric transfer hydrogenation. And again, probably just very briefly touch upon the biological activity. All right, so N-heterocyclic carbenes. And so from the purely organic chemistry perspective, a carbene is a divalent carbon. And in many cases, we can see the carbon has a lone pair that would be just superb for attaching to metals. And the specific case of heterocycles with nitrogen in them flanking the divalent carbon gives us the ability to stabilize some of these carbenes and make them even more useful as ligands. And back in 1991, Arduengo showed at the very least that if you put some pretty bulky groups to also flank that carbon, we can get stable, isolable, and structurally characterizable carbenes. And so in between are all kinds of substitutions that we can do on the nitrogen to tune the electronic and steric properties. And these become almost as variable as phosphine ligands for homogeneous catalysis. So in the first part, I'd like to talk about the synthesis and catalytic activity of these compounds and our particular way of investigating them. And then again, if time permits, synthesis characterization of the biological activity of some of these. Okay, so again, you can see that all of the things that I am showing here on the left, right here, are definite possibilities, or excuse me, definite ways that we can functionalize these carbenes. We can put extremely bulky groups around them. We could put some simple groups around them. We can make these chelating ligands. So our ability to customize these ligands is pretty not unlimited, but it's pretty expansive. And if you take a look at the literature of a lot of catalytic chemistry on the homogeneous front these days, people are finding ways to change these ligands to be redox active so that the redox activity of the ligand can supplement the redox activity of the metal. So in our particular case, we will start with the metal salts of either iridium or rhodium. And a good starting point is cyclooctadiene to make, on the right, as we show, these chloro-bridged dimers of cyclooctadiene metals. And we can then take those chlorides, exchange them for ethoxides, and those ethoxides serve two purposes. One is, again, as they keep this complex stable, but then they will also act as an internal base to deprotonate imidazolium salts to give us these bis NHC compounds. There are some literature references on this slide, as well as the fact that in our own hands, we've been able to get similar yields for these compounds. We do a fair amount of single crystal X-ray studies in our group because, that's one of the nice things about homogeneous chemistry, is that we can do some pretty sophisticated structural studies to tell how we can best design our catalysts, not only for activity, but for selectivity. And again, selectivity is often the hallmark of a homogeneous catalyst, especially in this case, we are talking about ultimate application for fine chemicals or pharmaceuticals. So once we've made the compound here with two NHCs, we discovered that these are iridium-1 compounds. There is what is essentially an oxidative addition reaction with amino acid to put a hydrogen hydride on the metal. Now we have a chelating amino acid dado group and our two NHC ligands. So now we have a octahedral iridium-3 compound that is set up very well for doing what I will be talking about in a little bit, the asymmetric transfer hydrogenation catalysis. The NHC, when it's methyl groups, we've been successful in adding just about every type of amino acid, from the simple non-optically active glycine all the way through some more substituted ones, including some of the ones that contain rings, such as proline. And proline, we will see in a bit, is one of the more important ones for the study. And we could also put other groups on the nitrogens of the NHC group and still get moderate to good yields of our amino acid compounds. One of the things that makes this both an intriguing and a difficult area of study is that these transition metal octahedral compounds already themselves have quite a number of isomers. And so if we only focus on those isomers in which the two NHC compounds are 90 degrees or cis to each other, we have, for even the simplest of the amino acids, we have two enantiomers, because actually we can have optical activity at the metal center. So we know enantiomers have identical properties, and nevertheless, they are different isomers. But if we do have optical activity at one of the carbons on the backbone amino acid, then we now start creating diastereomers. And that means that these actually do have different properties and therefore could be very different in terms of their selectivity in catalysis. Let's go to one more level of complexity. Again, notice I haven't talked about any other orientations of the two NHCs, only those that are cis to each other. And once we put something like proline on there, then we actually have three potential optically active centers. We've got the metal, we've got the carbon, and we've got the nitrogen. So we can have many different kinds of diastereomers. So it's not only a challenge for characterization, it's a challenge to figure out what we need for the optimum selectivity out of our catalysts. This just shows you how we can do at least one bit of characterization. As I pointed out, when we have glycine, we have enantiomers that have identical properties, and therefore all we see is one peak in the proton NMR spectrum. One of the things that's quite nice about hydrides on metals is that they show up in a region of the proton NMR spectrum that is well removed from anything else. So it is very clear when we have those, and we see one single peak because the enantiomers show the same chemical shift for the hydrides. But if we go to alanine or valine, two of the optically active amino acids, now we see two hydrides. And that's because we've got two diastereomers because of the optical activity of both the metal center and the amino acid. And finally, you can see on the bottom, excuse me, that's the L-proline complex. I mentioned that there were a lot of complexities because of all of the possible diastereomers. And you can see here that we do get an extremely complex proton NMR spectrum of the hydride. We'll see in a bit, at least I hope I can show the effect that has on the catalytic activity. So getting to the catalytic activity, let me very quickly explain that asymmetric hydrogenation certainly refers to the fact that if we start with a prochiral substrate and reduce it, we can get the optically active center at the carbon where we've done the reduction. And if we are successful, I mean, if we use just a normal hydrogenation catalyst, we will get a racemic mixture. We'll just get both of the enantiomers. However, if we do asymmetric catalysis, whether with H2 or, as we'll see in a moment, another surrogate for H2, we can get good optical activity in our product. We can choose one enantiomer over the other. For some smallish scale, it doesn't have to be that small scale, but certainly nothing on the order of the petrochemical industry. For the pharmaceutical or fragrance industries, using a hydrogen donor, such as isopropyl alcohol, we can actually literally pluck the hydrogen from the donor, use it in the reaction, and hydrogenate our substrate. Therefore, vessels of high pressure for hydrogen, and we eliminate the need to handle relatively hazardous H2 at high pressures. We can get good homogeneous catalysis to form a chiral alcohol. Let's look at the right first. On the y-axis is the enantiomeric excess, and that is simply defined as the percent of the major isomer minus that of the minor isomer. And in this particular case, something on the order of a 92% enantiomeric excess, literally means that we've got about 96% of one enantiomer and 4% of the minor. And we can actually do somewhat better than that, and we're now in the region where it is good for an ultimate commercial usage. One of the interesting things is that we see that at higher temperatures, we start off with somewhat good enantiomeric excesses, but then lose over the period of the reaction time. We need to study this because in some respects, it doesn't make a lot of sense from what we know. So clearly there's something worth pursuing there. But if we take a look at doing this reaction at 25 degrees, our enantiomeric excess stays very nicely constant during the time of the reaction. And if we go over to the left side, another thing that surprised us a bit is that we fully expected that we would need an elevated temperature, like 80 degrees Celsius, in order to carry out this reaction. And yet we discovered that, yes, it is a little slower, but not significantly so at 25 degrees C, so that, literally we can get very much the same conversion at about 12 hours that at either temperature. Also something that is worth looking at down the road a little more deeply. Base is important in this reaction because we actually need to deprotonate the isopropyl alcohol and give an alkoxide that will then attack the metal in the first step of generating the H2. And we find that there is an optimum at around 2 equivalents of base per metal catalyst. And we think that's because if you put way too much base in there, even though these are metal hydrides, they also have acidic properties. And so there is a fine balance between generating the active catalyst and actually deactivating the catalyst. So we need to stop at around 2 to 1. In terms of the amino acid that we use, so it's really the combination of the amino acid and the configuration around the metal center that gives us the selectivity, the enantiomeric excess. And so you can see that clearly glycine gives us no enantiomeric excess. And again, that goes back to the fact that glycine itself is not optically active. It does make 2 isomers about the iridium, but both of those are identical, and therefore we don't see any asymmetric induction. Alanine, we get actually only a very slight amount. And, it's kind of interesting because, yes, there is optical activity, but it's not enough to transfer to our substrate. Same thing with valine. And we found that it's really the ring-containing amino acids, even though they're extremely complex in the number of isomers they make. Proline turned out to be the best under a certain set of conditions. We get that 92% enantiomeric excess. And one of the very convenient things about these amino acids is that amino acids are relatively inexpensive. That's a good thing. They are abundant and variable. And we can change which alcohol we make simply by changing from the easily available L-proline, which will give us the R configuration at our product, to also abundantly available D-proline. We still get high enantiomeric excess, but now it is the S version. So we can get very nicely both enantiomers of our product, depending upon the system that we're studying and which one turns out to be more valuable. So in terms of these ring systems, we decided to look a little bit more closely at other prolines. I've already mentioned the L versus D. We were intrigued to see that you can, again, commercially available, get fluoroprolines, hydroxyprolines. Both of these gave relatively reasonable enantiomeric excesses, very good asymmetric induction, but overall their conversions weren't as good. We can maybe at least make an assumption now that the electron donating effect of the fluorine wasn't very good, but many, many more things must be happening here. So again, even though we have great control over what we do, the downside is that sometimes there are so many things to control that we're not quite sure how to take advantage of all of those. We were surprised to discover that changing the group on the NHC, these are the groups that are attached to the nitrogen, methyl group gave us our best conversion and our best EEs. These are all with L-proline. Putting an ethyl group on didn't affect the conversion, but it really hurt the enantiomeric excesses. Putting isopropyl on hurt both conversion and enantiomeric excess. A bit of a surprise initially, because we thought that a little bit more steric bulk on the NHC would give us some better selectivity, but that clearly tells us that we needed to think a bit more deeply about what gave us our selectivity. Looking at substrates, we actually had research prior to this, not NHCs, but cyclopentadienyl metal complexes with amino acids. And we found that those compounds were best giving us enantiomeric excesses for alkyl substituted ketones, such as pinacolone down below here. But we find that these NHC complexes give us better enantiomeric excesses with these aryl ketones. And so very different. And one of the things that we hope to be able to pull both areas of our research together is to describe what I call a toolbox that will allow researchers who want to do these asymmetric hydrogenations. They tell them, here are the ligands you could use, here's the amino acid, here are the conditions. And so we could hopefully contribute to the literature a wide range of possibilities. We try to do some DFT calculations on our compounds in order to try to understand all of the isomers that we get. And one of the reasons that we talk mostly about having our NHCs 90 degrees or cis to each other is that we find, let's see on this second row, even for the simple compounds with just glycine on them, that right here, for example, having the NHCs trans to each other are significantly higher in energy than the cis. And so we kind of think that we mostly have the cis isomers in solution, which we've also had mostly cis whenever we have done any kind of single crystal X-ray structure. Asymmetric transfer hydrogenation actually requires our ketone to come in such an orientation so that the carbon is attacked by the hydride and the oxygen coordinates via hydrogen bonding to the NH. And so what we see here is of all the different options of seeing the isomers that we can get for proline, which does give us our best EEs, is that there's only a few configurations where the hydrogen and the NH line up in a way that we could take that kind of advantage of. And therefore, that really does explain why I think we see good enantiomeric excesses, because even though we've got lots of other isomeric possibilities, they are not catalytically active. And so this shows what we would call the Enantio determining step. We've got the ketone, so that in the best of situations, the oxygen interacts with the NH, the hydride on the metal attacks the carbon. And we believe that an important part of this is what has been called in the literature is kind of a CHPI interaction, which is also why, number one, our best results are with these aryl ketones because of this interaction helping. And that's also why putting ethyl or bigger groups on the end seems to hurt our activity and selectivity, because we actually get our optimum interaction with a methyl group there. So we can make these complexes. They're very active. We can optimize them. And to be honest with you, there's a lot more that we could do on these systems, and hope to be able to dig into them in the future. Javier, how much more time do I have, please?
You have 8 minutes or even more if you want. Yeah.
Okay.
8 minutes. Yeah.
Yep. All right. I will definitely take just a few more minutes. I'd like to talk about a different set of NHC complexes, this time with what we would call is pentamethyl cyclopentadienyl, and their ability to attack microbes that are currently a problem because of antibiotic resistance. The World Health Organization has indicated that the number of multi-drug resistant forms of tuberculosis, for example, worldwide is enormous. In the United States alone, the CDC has shown that there are quite a few emerging pathogens that are antibiotic resistant. And so we actually began, I think I told you that we were doing research on these cyclopentadienyl compounds with amino acids for asymmetric transfer hydrogenation, and indeed they were. But we also wondered, we've got these biologically relevant ligands. Could we find biological activity for them? And we were very fortunate that a colleague in the biology department, a microbiologist named Joe Falkenham, said, oh, sure, I would like to study them. And we found that one set of compounds, these amino acid compounds, were very active against a mycobacterium, M. smegmatis, and other mycobacteria, including tuberculosis. We found that a different set of complexes were effective against Staph aureus and its methicillin-resistant forms known as MRSA. In 2018, Dr. Chrissy Duchesne and my group found that we got even better activity against some mycobacteria with acetyl-acetonate compounds. And so we decided we wanted to take a look at what would we get when we had these NHC compounds. So now we're not looking at them for their hydrogenation activity, but rather their biological activity. This just again shows one of the reasons we like these, both for catalysis and for biological studies, is the variations we can make of them. And especially in biological activity, we're always looking for structure-activity relationships. So what happens when we change one group? Do we lose activity? Do we gain activity? And so these are functionalizable on the NHC, a lot of functionalizability on the NHC, and on the ring system. And so here are all of our kind of, at least what we have sampled so far in terms of activity and functionalizing. Professor Falkenham, my colleague, he's always very nice about looking at a broad panel using Staph aureus and the methicillin-resistant form, E. coli, a microbacterium, some yeasts, and some other things. And we found that these rhodium and iridium complexes gave us our best activity against mycobacteria. Again, we can't, or Dr. Falkenham can't test TB in his laboratory because that requires a higher biological safety level, but he can test some mycobacteria that act as surrogates, and then we can send them to different laboratories for direct testing of against TB. And we can see that in many cases, we are close to what one can get with something like streptomycin. And if they are resistant, then we don't have that problem. And again, if we compare our different NHCs and what's on the piano stool, we get some excellent activities against these mycobacteria. This is a little bit different in terms of micromolar as opposed to some of our previous slides that were microgram per milliliter. But you can see that by putting, maybe just a little more hydrophobic character onto the ring, we get better activity, lower being better. On the right side, by the way, that's the dimer, the chlorobridge dimer we use to create these. And so just to show that the whole complex is responsible for activity, we show that our dimers are nowhere near as active as our NHC complexes. So structure-activity relationships, we can change this ring up here. We can change the NHC, we can change the metal. And so rhodium complexes display better overall reactivity, but one of the iridium complexes, where this R was a phenyl group, as I mentioned, is the most potent antimicrobial agent we have found in our study so far. We do get some enhancement of rhodium complexes, and the NHC shows that we can do some nice improvements of activity by also putting like a cyclohexyl group on the end. So we've made a modest library of rhodium and iridium CP star NHC piano stool complexes. They show promising antimicrobial properties against M. smegmatis and some others. And we are starting to unravel what we would call those structural activity relationships, and giving us some guidance as to what we can do to improve further. And so again, both catalytic activity and biological activity are part of these packages that we're dealing with. And Dr. Christine Duchesne and Dr. Chad Bernier, I've mentioned, previous workers at the graduate level, all having their doctorates now. Undergraduate researchers and collaborators have all been wonderful in helping us move this along. And the one little tantalizing tidbit I will throw out there is that one subset of what I talked about today has turned out to show excellent activity against SARS-CoV-19, our current pandemic causing virus. And we have a paper ready for submission on that, and I'm looking forward to learning more. So, questions, and thank you once again for allowing me this opportunity.
Okay, thank you very much for the talk. So any questions from the audience? So, okay, I have a question because I think, well, thank you for the talk. It was really interesting. And I think the antibiotic resistance was also quite challenging. So, I mean, you mentioned at the end that you were also studying the possibility of COVID, and what are the next challenges that you will face in terms of the antibiotic resistance and maybe the COVID as well?
Well, there are two challenges. Well, no, many more. But the two major challenges are, number one, we are finding it a challenge to get significant funding because there is a great prejudice that only natural products can be used in these regards. We have tried very carefully, I didn't talk about that today, but we have tried to show and have shown that in vitro studies using mammalian cells, including human cells, show that these compounds are not toxic to those cells. So that's obviously step one. And in one study, which unfortunately these are expensive, so we haven't been able to do a lot, but one small animal study using rats showed that they were not harmful at all to a mammalian small animal. Nevertheless, we keep hearing back from reviewers of proposals that, oh, these are going to be toxic. So I keep hoping to tell them, well, fund us and we'll show you it isn't, but okay. The second challenge is of course, who is going to develop these on a commercial sense, especially for the bacteria, because pharmaceutical companies, to be honest, they want profit. And if these are ultimately go through the whole rigorous process of getting approval, they would be last resort methods that would sit on the shelf until all else fail, which means that unlike things like high blood pressure medication or cholesterol medications, which you have to take every day, these would not be taken very often. Therefore, they would not sell a lot, and therefore they wouldn't get their profit on it. So those are the two big challenges.
Okay, thank you. Any other questions?